Everyone, we're going to get started. Our goal today is to finish off definite integrals, which are these three here are the last three. And then we'll move on to the next section, which is split into two parts. The part we're going to do is part A, and it's going to be finding what's called an indefinite integral. And the good news is that they're virtually identical. The two types of questions, definite integral and indefinite integral, share a lot in common. So, what is left for us to do? Well, there are three examples at the end of our section. Let me get the number for us to remind myself. Section 5.3, the fundamental theorem, where we've been asked to find the area under this curve, and this curve. And what I had to do is I've had to add some more antiderivatives to our list of things that we have the antiderivatives for. So let's start with the first one. 1 over 1 plus x squared. Its antiderivative is the inverse tan of x, sometimes called arctan of x. And I know it's a while since you did some of these, and you probably didn't do that many of them, but if you think back, isn't the derivative of the inverse tan 1 over 1 plus x squared, right? So that is true. Now, the second one is probably even rarer than that one, but the antiderivative of 1 over the square root of 1 minus x squared is the inverse sine of x. Right? Just telling you that off the bat, it is. Go back and look at your derivatives. If you differentiate an inverse sine, you get that. You probably only did, what, 4 or 5 questions, but it was part of the things that you've covered. Now, the last one is not the same thing as x to the power of 2 or the power rule. This is a to the power of x. So this will be things like 3 to the power of x, 5 to the power of x. And the antiderivative is a to the power of x, the original thing, divided by the natural log of a. So for instance, the antiderivative of 3 to the power of x is 3 to the power of x, all divided by the natural log of 3. E to the x is a special version of this rule. If you did e to the x, then the rule would be e to the x divided by the natural log of e. But isn't the natural log of e 1? So you get e to the x plus c, right? You get what you always did. So e to the x is very special case, right? Typically, 2 to the x, 10 to the x, you need this extra natural log of a bit added on to the antiderivatives. So that's the first piece of the puzzle. Let's look at how we would tackle it. So the first question is a version of question 22. And we're going to find the area under this curve, this definite integral as we call it, of 5 over 1 plus x squared dx. And I know that 1 over this is an inverse tan, so 5 of them would get me 5 inverse tan of x. And then you'd evaluate it at the start value and the finish value. And now we have 5 inverse tan of square root of 3, take away 5 inverse tan of 1 over the square root of 3. And unfortunately, a lot of people just want to leave it like that, saying, hey, I've got your answer, what do you want? Well, I can take it a bit further. The inverse tan of 3 and the inverse tan of 1 over root 3 are in fact numbers. We get these guys from the unit circle. So a little side issue. When someone says to you, what is the value of 5 inverse tan of 3? Let's just focus on the inverse tan of 3. What we're looking for is some angle in the unit circle, we'll call it theta, that has the property that the tangent of theta is the square root of 3. So the inverse tan of 3 is an angle whose tangent would be root 3. And the unit circle is designed really well for finding sines and cosines and cotangents. Really good for those. It's not really designed very well for finding inverse anybody, right? So you have to do a bit more work. Now, if I look at the candidates for this angle, right? When will I get a tangent or inverse tangent of root 3? I'm looking for one of these three angles here whose tangent would be root 3. Now, if you look at the values, the y divided by the x, right? Because that's what a tangent is, y divided by x. I've got this guy or that guy. This guy here is not going to work. Would you agree that that divided by that gets you 1? So I've now got 2 to choose from, and you can simply just guess. Let's try pi upon 6. Well, I wonder if the tan of pi upon 6 is that number, in which case I'm done. Well, it's going to be 1/2 the y divided by root 3 upon 2. And can you trust me, after a little bit of tidying up, it's that one. Which means it's not the one I'm looking for. Well, the other choice was pi upon 3. Well, the tangent of pi upon 3 is the y coordinate divided by the x coordinate. And yes, bingo, it's pi upon 3. Right, so if the tan of pi upon 3 is this guy, the inverse tan of root 3 is pi upon 3. Do you see it's like a two-way street? So I now know that guy. If I want to find the inverse tan of 1 over root 3, I've actually found it accidentally up here. It would be pi upon 6.
There's a ring light on my camera.
So are we okay with this kind of almost haphazard way of finding inverse tans? Right? You have to kind of look at your choices and then pick some and see which one works, or just have a really good memory. I guess that works too. So back to our question. 5 inverse tan of 3s is 5 pi upon 3s. 5 inverse tan of 1 over root 3 gets me 5 over them. I have 5/3 pi, take away 5/6 pi, which leaves me with 5/6 pi, and we are done. So this integral is equal to 5/6 pi, and that's one of our 3 challenges out the road. Here we go. Let's look for our second one now. Question 23 is asking us to find the area under the curve from 0 to 3 of 6 to the power of s ds. And I recognize that that guy is one of these. Right, it's this guy here. So its antiderivative is 6 to the power of s divided by the natural log of 6. It's a bit like just memorizing some things. This is one of these, you know, these 3 here especially, you just can't memorize them. Now, I can evaluate these at 0 and at s equals 3. So I'm going to get 6 to the power of 3 over log 6. Take away 6 to the power of 0 over log 6. And 6 to the power of 3 is 36 times 6, 180, 216. And 6 to the 0 just gives me 1. And since these share a common denominator, we can put them together. And there's your answer. So the area under this curve would be that. Now, if this was 2 to the power of t, 5 to the power of x, it wouldn't look that much different, right? Any questions on that second one? Are we good? So that's how you're going to tackle 2 to the x, 6 to the s, whatever. Right. Last one, 24, and then we can start our final section for this week. Three over the square root of 1 minus x squared. Well, the guy that matches with is this one here. 1 over the square root of 1 minus x squared is an inverse sine function. So 3 of them will get me 3 inverse sine of x. And then we're going to have to evaluate it at 1 and at 1 over root 2. That's going to get me 3 inverse sine of 1 over root 2. Take away 3 inverse sines of a half. And I need to find the exact values of them, which means I need to go to my unit circle. The inverse sine is a little bit easier. What I'm looking for here, for instance, is an angle whose sine is a half, and the sine is the y coordinate. So I'm looking for an angle whose y coordinate is a half, and yay, I'm picking it, pi upon 6. So 3 times pi upon 6. And this angle, an inverse sine is really an angle. I'm looking for an angle whose sine is 1 over root 2. So I'm going to look for a y coordinate that's 1 over root 2. And superficially, it looks like none of them match. Right? None of these 3 y coordinates that my finger is pointing at, none of them is 1 over root 2, or at least looks like it. But if you look again, isn't the square root of 2 over 2 the same number as 1 over root 2, right? Can you imagine taking this and multiplying top and bottom by root 2, you get that. So this guy is actually the angle pi upon 4. These guys have to be in the unit circle, so I know it had to be there. So what have I got? I've got 3/4 pi, take away a half pi, and that leaves me 1/4 pi. And so we've done an inverse tan. We've done a 6 to the power of something, and we've done an inverse sine. And that kind of covers everything that happened in section 5.3. Is there any questions before we go into 5.4 then? Feel good? Okay. 5.4 coming up. Just put my little heading down. Math 152. Section 5.4. And it's called the indefinite integral. And it's split into 2 parts, so we're only going to do part A. Next week we'll do part B. Well, the good news is very little extra work. In fact, in a lot of ways, a lot less work. We already know how to find antiderivatives to get integrals, right? If I give you an integral and I said to you, the integral from 1 to 3 of x squared plus 5x minus 1. We call this type of integral a definite integral. And a definite integral represents the area under a curve, and this will equal, when we're finished, a number. It could be 7/11, it could be minus 20. It's a number. If you wanted to do it, just like we did yesterday, add 1 to the power row. Add 1 to the power row. So you find the antiderivative and you put it here, and then you would evaluate it at x equals 1, at x equals 3, and you'd get whatever you get. That is a definite integral. We are going to be dealing with integrals that look like this. And the only difference is, do you notice that there's no limits of integration here? It's just the integral sign. but no 1 to 3 or 2 to 7, right? When you see that, we call these an indefinite integral. It's their name. Now, the solution to this is find the antiderivative. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. The only difference is that in an indefinite integral, you always have a plus c in it. Remember yesterday someone was saying, why didn't I put plus c's when we did these guys? And I said, well, technically you could, but since the first one kills off the second one and it always disappears, we kind of don't bother. But in an indefinite integral, that plus c is part of the result. It's part of the answer. So if you don't put it in, Weber sign, and all you type is what you see there, Weber sign will say you're wrong. And it should, because that's it. So in a way, isn't an indefinite integral just another way of saying, tell me the antiderivative of the thing, right? Tell me the antiderivative of this thing. That's essentially what an indefinite integral is, which means then that all the kind of tricks that we used yesterday to find antiderivatives, we are going to use them here. The good news is that we won't have to plug numbers in and spend 3 more minutes finding out the answer is 7/11ths. Once we find the antiderivative, don't we just say plus c and we're finished? So they are less work, right? They're easier to do because there's less to do. And let's jump right in and I'll try some of the typical kinds of questions that you get. And there's all sorts of ones. Oh, I'll keep my list of antiderivatives handy because we'll use them. Let's start with this one. In a question like that, do not overthink it. Isn't this guy good to go? Can't I just use the power rule to get each of the pieces and I'm done? So add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Add 1 to the power and divide by the new power and finish with a plus c. That's how quick some of these questions are going to be, right? One-liners. Why is that -1/2 and not -2/4? It's a kind of silly question, but I am asking it. Why do you write -1/2 here and not -2/4?
1/2 is the same thing as 2/4.
And isn't it normally regarded in mathematics without being told that shouldn't you simplify fractions, right? It's part of the style point rule. In fact, there are only 2 style point rules. Make it look like the original, right? So if the question had square roots, I want square roots. And the second one is, tidy it up, right? Don't leave things as 4/8, right? That kind of thing, right? Now, that would be great if that's the only question that you got, and that's fine because there are questions. That one, for instance, is not the same as, but it's very similar to question 1. Now, how about a question like this? Now, this one isn't a power rule, but all the pieces exist, right? We know what they're equal to. Now, if you've got a good memory, you've memorized them by now, but if not, you would go and look at your table. So let's find each piece. What is the antiderivative of 3 sine x?
3 negative cosine x.
Okay, and I'll stick the 3 at the front because it looks prettier there, okay? What is the antiderivative of 4 secant squared x? It's over here somewhere. Antiderivative of 4 secant squared x.
tan x.
Okay, so 4 of them get you 4 tan x. And isn't e to the x, so you get that guy, and you finish with a plus c. See how easy it is? If you have a good memory, if you've memorized these guys, you don't need this anymore. You can just boom, boom, boom. Nothing was necessary. It was good to go. It was just a matter of finding its antiderivative. Now, that isn't going to always be the case. So here is an indefinite integral. We want to find its antiderivative. But you cannot find antiderivatives if you leave things as cube roots and square roots, right? We know that doesn't work. In fact, anything that involves this type of shape, isn't it going to have to be a power rule, which means you're going to have to rewrite them as fractional powers of x. So this cube root is going to be called x to the 1/3. And a little bit sneakier here. That square root is a half power. I agree with you. But it is on the bottom, isn't it? It's 4 over the square root of x. Well, are you happy about why that's negative a half because of that? Now, once you have got everybody that is in your question turned into, in this case, powers of x's, can't we just use the power rule? So we'll add 1 to the power. We get 4/3. You then divide by that new power. Dividing by 4/3 is the same thing as multiplying by 3/4. So that's why that's 9/4. Now you add 1 to this guy, add 1 to negative a half, and you get a plus a half. And then dividing by a half is the same as multiplying by 2, which is why that guy is 8. And then you add c. And like every question, and I'll probably say it 100 times before we finish this quarter, style points, style points, style points. I don't need to worry about the numbers, they're good. But these are fractions, and these are not. These guys have to look like these guys. So 4/3 means it's a cube root of x to the 4. 1/2 is a square root of x, add c. And now we are finished, right? Style points. So, side issue. Why do I bug people about style points? Why do I keep saying, look, you're not finished when you're here? Oh, by the way, which is really annoying, but I can't stop it. You could probably type that into WebAssign and it'll give you the points. Because WebAssign isn't a human being, and WebAssign has been programmed to a level that's probably not perfect. But this is the correct answer. Why am I being so fussy about the way an answer looks? Mathematics is a very interesting subject. One of the things about it is that in a lot of ways it's a language. It's a way for us to communicate concepts and ideas, right? Functions and properties of functions. And one of the things we have to try and make sure that we do is that we all play the game the same way. So mathematicians, through experience, have came up with rules about what you write and how you should write them. And we use a lot of these rules even today. If I said to you the answer was 1x plus 7, would you agree that almost everybody would write x as 7? Don't we have a rule? 1x, you don't need the 1, you call it x. If it was 0x squared plus 7x plus 1, would you agree that we would all write 7x plus 1? Because there's a rule that says if you don't have something like 0x squareds, don't write 0. Don't even write anything, just write what's left. We have rules like 3x to the 1 should never be written as 3x to the 1. Shouldn't it be written as 3x? Now, because we have all these rules, I could give that question, that's the exact same question. It would be written the exact same way to a Frenchman who doesn't know one word of English. But I could write that down to a Frenchman. And that French person would do the same things that we did. And that French person would finish with the same answer. You know, you don't want some countries to do this, some countries to do that, some countries to do some other thing. Because then don't you have the problem of, well, is my answer the same as your answer? Because now I'm going to have to figure out, does my answer eventually become your answer or vice versa, right? Everybody uses the same rules. Everybody is consistent. Everybody's happy. So I can do math with someone in China. I could do math with someone in France. Even if I can't speak their languages, which I can't, couldn't I still write down the math and they could follow what I'm doing and we'd all agree that my answer was the same answer they would get? That's much more difficult in almost any other world, right? Because don't your own language interfere with it, right? You have to write English when you write physics things down, right? You have to describe the properties, not just by formula, which is where we come in, but using English. So I'm pernickety because it's important. What would you do with this question? Tell me the first thing I would need to do to this question before I could do the antiderivative, which would probably be a power rule.
Foil?
You'd foil. And isn't that pretty much kind of what we did yesterday, didn't we? We done questions like that. Wasn't the only difference, it was from 0 to 4. So once you've foiled it, you add 1 to the power, divide by the new power. You add 1 to the power, divide the new power. Boom. Done. What would we do this time? And we did come across a question not unlike this yesterday. So do exactly the same thing that you would have done yesterday. How do we fix this guy? Because right now we can't get its antiderivative. So there's a clue. What would I multiply it by?
Isn't it x to the negative 1/2?
You nailed it, Vanessa. It is x to negative a half, right? Square root in the bottom, negative power on the top. Now you multiply each of these, you get what, 3/2. You multiply this one, you get 1/2. And you multiply this guy at the end, you get negative a half. Do you see now you can use the power rule? Right. If that guy was x, just argument's sake, suppose it was x squared plus 5x plus 1 over x, wouldn't we multiply it by x to negative 1? If that guy was x cubed, wouldn't we multiply by x to the negative 3, right? So same process, slightly different values. Now, for completeness sake then, add 1 to the power, divide by the new power. Add 1 to the power. Well, dividing by 3/2 is the same as multiplying by 2/3, so you get that guy. Add 1 to the power, divide by the new power gets me that. And we are here. Are we finished? Is that the final answer? Nope. Don't we have style points? Didn't the original question have square roots in it? Since the original question had square roots in it, we get this guy, we get this guy, we get this guy, and I'd say. I want to show you an identical question, identical mathematically at least. Do you notice that in this question, the square root has been replaced by an x to the half? which is the square root of x. When you do this question, you'll end up with the exact same answer because it's essentially the same question. But according to style point rules, isn't this the right answer? Do you see the difference? There's fractions in the question. There's fractions in my answer. There are square roots in my question. I need some square roots in my answer. Right, so you see, context decides what style points want you to do. How about this fella? Weird function. You don't see x to the power of 1.3 very often. Well, add 1 to the power. I mean, it's good to go. I can use the power rule. Add 1 to the power and divide by the new power. Add 1 to the power and divide by the new power. I'm happy with that answer. I know it looks ridiculously ugly, but wasn't the original question just as ridiculously ugly, right? See, fractional pairs, decimal pairs, decimal pairs. I guess if I wanted to, I could try and tidy these up, but I'm not sure I would get much out of it, right? You know, fractions with decimals in them are not pretty at the best of times. Probably wouldn't turn into anything useful. But that's
Is
good.
the bottom 0.1 or 0.7 or is it 1.7?
I think you caught my deliberate mistake, Vanessa. Actually, it's just a mistake. I don't do deliberate ones unless I tell you. Yeah, 1.7. Are we getting the feel for the process is very similar to yesterday, right? You know, do what you need to do to get it into a form that allows us to be able to find antiderivatives. Okay, how about this fella? First things first, I do not need to do anything to these three guys. I don't need to rewrite them as, I don't know, 1 minus x squared to the power of negative half. I do not need to algebraically change them at all. And the reason for that is that each one of these pieces has an antiderivative. So let's start with the first one. What is 3 over 1 plus x squared? What's its antiderivative?
Three inverse tan.
Correct. Okay, -2, I'll put the -2 part in. What's the 1 over 1 minus x squared antiderivative? What's the antiderivative of 1 over 1 square root of 1 minus x squared?
Inverse tan or inverse sine.
Agreed. And this guy is that guy. So it's 3 to the x over log 3 add c. Now, in a question like this, I don't have any style point issues because there's not really anything I could change it to, right? Because the answer doesn't look very much like the original, right? So there's no clues about what you should change it. And this is totally acceptable. This is the answer. Now, I'm going to show you an issue with WebAssign. Oh, somebody might have given an answer. Yes, you did. And someone did exactly preempt what I'm about to show you. Eventually, once I hit the right buttons. Right. Let's suppose I was doing question 6, right? Well, add 1 to the power x cubed, divide by the new power, and that would get me 4/3. And then I would have what, x cubed. We don't want capitals, so x squared. There we go. The number 2 would just get me 2x, nothing wrong with that. And this guy would get me 3 inverse tans, right?
Oh, we aren't able to see the screen.
Oh, thanks for telling me that. I should normally ask that. Right, so add 1 to the power, 4/3 x cubed. The 2 gets me 2x. Now, if you want to do the inverse tan, right, 3 times inverse tan, you'd go 3. And WebAssign doesn't want you to type in tan to the power of -1. I think if you try that, it'll just get really annoyed and not know what you mean. So hit the trig button, and then you can pick inverse tan and just put your x in. Right? That's the simplest way to do that. There is another option, the inverse tan. Oops, I'm in capitals again. If you type in arctan of x, it's the same thing as the inverse tan, right? So some of you may have, I don't like arctans, but some of you might be comfortable with it, right? The simplest thing is just to make sure that you hit the trig button, in which case you can get inverse tan, inverse sine, whatever you need. Okay. Since we're here, let's just talk through some questions. Question 7 is good to go, isn't it? You can just find the antiderivative using the power rule. Nothing else to do there. What would I change in question 8? How would I alter this so I could find antiderivative? Oh, someone's already beat me to it. No is the answer to Ginger. But what would you do here? I mean, I can't do the power rule on that. I need to do something. I need to change its calculation. So while you're thinking, I'll set it up. You're going to do 3x squared plus 2x plus 1. And what you're going to do with that 3x squared plus 2x plus 1.
Times x to the -1.
Yeah. So you're going to do x to the power of -1, right? And I'm going to see what that's equal to. Well, 3x squared times that guy gets me 3x, which is good. 2x times x to the -1, essentially you just get the number 2. And the last guy, you get x to the power of -1. And everything's looking good, right? That's what you'd get. And I can integrate the first 2 terms. That guy I can integrate. It's got an antiderivative. That one I can do. If you try to do the power rule on that guy, it's a very special case, isn't it? If you try and do the power rule on x to the -1, you get x to the 0 and divide by 0. And the reason for that is that this guy is better to be written like that. So you're going to get 3/2x squared plus 2x plus a natural log of x plus c. Right, so everybody can be done as a power rule except x to the -1s, right? X to the -1s are a special case. Okay, this one is good to go. Can someone tell me what the antiderivative of that guy is? Okay, I'll nip over to the whiteboard. What is the antiderivative of that guy? The variable p is totally irrelevant. 5/1 plus p squared. What's its antiderivative? Oh, somebody's got the answer. I hope.
Inverse tan.
Inverse tan or arctan if you prefer. Now, this one has limits of integration. So it's not an indefinite integral, it is a definite integral, which means we're going to, when we're finished at least, have some numbers. So it's going to be 5 times the inverse tan of 1, take away 5 times the inverse tan of 0. And to speed things up here, the inverse tan of 1 is the angle whose tangent is 1, which happens to be 5/4. And inverse tan of 0 is the angle whose tangent is 0, and that angle is 0. And so what you end up with is 5/4 pi. Now, if these two guys were missing, the answer would simply just be 5 inverse tan of p plus c. So that would be the indefinite version. And the ones with numbers, this one here, is the definite version. Make sense? Right, so we're now mixing and matching definite integrals and indefinite integrals. I'm not going to do question 10, I'm just going to start it. So it's 2 cube root of x's plus 5, that's meant to say 4, 4th root of x. That's who we've got to deal with. Any suggestions about how to change the way this looks so that we could eventually get antiderivatives? Is there anything we can do about writing this in a different form that would enable us to get antiderivatives?
Start by distributing the x.
We will, but what about this cube root of x? Should I write it in a different format first? So what should I call
2 times 1/3 x.
it? Okay. And this one is 5x to the 1/4, right? And then, as you say, distribute the x. So it's now 2x to the 4/3 and 5x to the 5/4. And then you can do the power rule and everything is hunky-dory. And someone, Anthony, you're right, done it into fractional powers. Let's return back to the homework questions then. Some questions are as simple as they look, so don't overthink it. How would I rewrite the 4th root of x to the power of 5 so I could get its antiderivative? What would you rewrite the 4th root of x to the power of 5 as? Someone in the chat? Correct. So you're right, Nathan. 5/4. Right? X to the 5/4. Then you can do a power rule. And this question here is good to go, right? Isn't it just a whole load of power rules? Don't need to do anything. This guy here, there is an issue. It's a very minor one, but it is annoying. Let's do the antiderivative of e to the x is e to the power of x, which is pretty straightforward. No issues. The problem I have is this guy. Let me tell you what the answer is not. Oops, wrong one. It's not that guy. So maybe picking up an awful lot of brackets. Not one. Nah, it's not that guy. 1 over x gets you the natural log of x. That is correct. But 1 over 2x does not get you the natural log of 2x. And 1 over 10x doesn't get you the natural log of 10x. You have to think of this guy a little bit weirdly. You have to think of it as 1/2 of 1 over x. So 1/2 of 1 over x. And that's the guy that you get. Does that make sense? that the 1 over 2x has to be kind of looked slightly artificially, but it's the only way you can get it to work. And then you can add your sign. And perfect timing. Tell me what you should do in the final question 15 to get it into a format that would allow us to find its antiderivative.
Foil it.
I agree, foil it. It's not your typical foil, but it is foil. So, question looks something like 2 plus r over r squared. Normally when you have a foil, you just have that guy, right? 2 plus r. So I'm going to rewrite this fella as 2 plus r over r times 2 plus r over r. And then the 2 r's on the bottom get me r squared, and this is overkill. You don't need this many lines. So that's essentially what you have. Now, if you foil out the top, you get 4 plus 4r plus r squared over r squared. So that's like phase 1 done. We're kind of halfway there, but we're not finished. And this has happened at least 2 times, maybe 3 times today, and certainly a couple of times yesterday. You need to do something to this algebraically so that we can write it down in a way that will allow us to essentially use the power rule. So what will this turn into? Here's a clue. What will I multiply that top guy with?
Part of the negative 1/2.
Right, that guy. Good. Now, that gets me 4r to negative 2, 4r to negative 1, and this guy times this guy gets you 1. And everything is looking good, except for one term. Which one of these 3 guys is the only one I cannot use the power rule on, and I'll have to rewrite it in a different form so I can find out what its real antiderivative is? Which one of these 3 you can't use the power rule on?
4r to the negative 1.
Right? You've seen that before a couple of times, right? So that means whenever you see something like that, you immediately fix it, and then you do antiderivatives. Add 1 to the power, divide by the new power. This guy in the middle becomes 4 logs, and this guy becomes an r, and there's we've got a c. And like every question that I've done today, even although quite a few of them we didn't need to do anything, I still ask myself style points. Is that the right version of the answer?
No.
No. My question did not have any negative powers in. So I'm going to make it that guy. Okay, it's just a little cosmetic thing, but it's important. Oh, and a second feature. Do you know if this one hadn't been an indefinite integral? But let's just say, for example, that this thing here actually had some numbers on it, right? It was a definite integral. If you write the guy this way, and then you replace r equals 1 and r equals 2, won't this fraction be much easier to deal with than minus 4, 2 to the power of negative 1? Can you imagine just what is that? You know, you wouldn't really be able to figure it out easily. You put it in here, isn't it? Minus 4 over 2 and minus 4 over 1. Hey, no problem. So style points very often can help in calculations as well. put your last name down for attendance, and while you do that, I'll tell you some housekeeping things. Your test 2 is now, online test 2 is now visible. All the homework from week 1 and 2 is due this Sunday. So if you've already done weeks 1, you don't really need to worry about it, but it's there if you want to go in and maybe tweak some of your answers if you suddenly realise that you now know how to do something that you might not have known last week. You've got test 1 and test 2 and all the homework, and its drop dead date is Sunday midnight. And do the best you can. Don't do the test until you are ready because it's timed. And what else did I mention? I will see you all on Tuesday. I am so looking forward to it. Emery, I'll be able to tell you some of my best jokes when I see you. You looking forward to that? No, I tell really corny jokes, by the way, so you might not look forward to it. But it's Tuesday, I will see you. On Tuesday, will you remember to bring, I know it's been ages, Project 1, because I'll now physically be here and you can hand it to me physically, right? So that's it. I'll hang about for any questions. Apart from that, bye-bye. See you Tuesday.
I did actually have one question.
Sure. What's the question?
I was doing trying to do the error calculations for the midpoint one,
Yes.
and I found the formulas in the book, but they.
Oh
I
God,
know if
don't
those-
use that thing.
Oh, okay.
I mean, when you look at that formula, it's scary. Plus you have to
Yeah,
estimate it.
yeah.
Yeah. So all you're going to do instead is find the exact value by just plugging into your calculator. So let's
Okay.
suppose that you had, I have no idea. Let's suppose you're doing that guy from 0 to 2, right? And I'm making this
Mhm.
up. And your estimate was, let's say, was 3, right?
Okay.
And you do that in the calculator and you find out the right answer is 8/3, right?
Mm-hmm.
Then the error, let's say we did it using trapezium 4, right? Then the error in the trapezium is the real value, take away the estimated. And so in this case, the error would be 2/3.
And that's the whole thing.
That's the whole thing.
Okay. That makes a lot more sense.
Well, I mean, we have calculators today, so I
Mhm.
don't see why we shouldn't use them to get the exact value. If you use the formula, you're probably talking about a formula that looks something like m b minus a to the n over n factorial. Yeah. And m has to be the estimated maximum value of whatever it is, the fourth derivative or something.
Mm-hmm.
Oh God, that is such a horrible formula.
Yeah, it was like the second derivative times like
Yeah.
the maximum value. Yeah.
Yeah.
It was
You
kind
can
of-
get actually you can get a much more accurate answer
Okay.
because the calculator will tell you what it is.
Yeah.
And what they would do is that would get replaced by that thing that we don't want to do, take away 3.
Okay.
And actually, I think they put the whole thing together in one big formula, so you just do the whole thing in one go, and it tells you the error. But it's still not the way I would tackle it.
Thank you.
Okay. Right.
Have a good day.
Okay. Bye, bye, guys.
you
Unless there's any
Tuesday.
more questions. See you Tuesday.
On the homework for 5-2,
Right. So 5-2. Is that what you just said? Adrian, was it you that had a question on 5-2? No. Okay, I misheard. Right. Well, bye bye. If you have any questions, I'll see you later. Office hours at 11 today. You can drop in then.
I did have a question for 5-2.
Okay. What is it?
On the first question, part F, the integral starts at 10 and ends at 0. And the video that goes with it didn't explain how you're supposed to do that.
5-2 question 1.
Yeah, part F.
Part F. It's if I'm looking at part F, what I'm saying is this guy here. You tell me if that's the same question. No, that's the wrong place. You tell me if this is the same guy that you're talking about. Damn it, I've got so many buttons here. I don't know which one I'm closing, which one I'm opening. Right, let's try that third time lucky. There. Are you talking about this guy here?
Yeah.
Now, normally you would start with the small one and finish with the big one, because that's kind of the sensible way to do this. So if you go here and you start at 0 and you finish at 8, you're finding this area here that I'm trying to outline as my mouse moves. Do you see it there?
Yeah.
Now, the bottom box is what, 4 by 8, so that's 32 for that piece. And a half of 8 times 8, so a half is, that is 32. Okay, so it's 64. So if you're going 0 to 8 with 64, if you reverse the order, you just get negative 64. So essentially, limits of integration, if you do them in the normal order, then the answer that you get represents the area under the curve. If you switch it so that you put the big number first, right at the bottom, and the smaller number at the top, the net effect is that you're doing things backwards. And that backwards process makes all the answers change. So a plus becomes a negative and a negative answer becomes a plus. So if 0 to 8 was 20, 8 to 0 would be negative 20. If 0
Okay.
to 8 was minus 4, 8 to 0 would be plus 4. So if you go